Welcome to The Explainer. Today, we are unpacking an absolutely fascinating piece of neurobiology. This explainer is named after the study we're diving into, the 2009 paper by Amy F.T. Arnsten, titled Stress Signaling Pathways That Impair Prefrontal Cortex Structure and Function, published in Nature Reviews Neuroscience. If you've ever had that terrible experience where your mind just goes completely blank during a high-stakes moment, well, this paper explains the exact, literal biological mechanisms behind why that happens.
So let's dive right into this by starting with a very relatable human experience at the macro level. The author points out a pretty devastating historical observation, and I'll quote the paper directly here. Pilots who were highly skilled during peacetime often crashed their planes in the stress of battle owing to mental errors. Think about that. It wasn't a loss of physical ability. It was a profound, sudden loss of complex cognitive function right in the middle of a life-or-death situation. What exactly is going on in the brain when acute stress completely overrides years of intensive, ingrained training?
Here is our roadmap for today's explainer. 1. Stress hijacks the brain. 2. PFC versus amygdala control. 3. Testing spatial working memory. 4. Cellular chaos in the brain. 5. Inside neurons under stress. And finally, 6. Mental illness and society.
Let's get right to section 1. Stress hijacks the brain. Losing the mental sketchpad. To really understand this deficit, we first have to look at what's normally working. For that, we reference the foundational 1996 study by Goldman-Rakich, PS, titled The Prefrontal Landscape: Implications of Functional Architecture for Understanding Human Mentation and the Central Executive, which was published in the Philosophical Transactions of the Royal Society of London, Biological Sciences. This paper essentially defines working memory. To quote the research, it's the ability to maintain a mental sketchpad to protect fragile representations from interference and regulate behavior, thought, and emotion. This crucial, delicate holding of information happens right in your prefrontal cortex, or PFC.
Moving to section 2, PFC versus amygdala control, the brain's shift in power.
You see, these two brain regions are basically in a constant tug-of-war for control over your actions. The absolutely crucial point here is the contrast between what we can creatively call the delicious cycle and the vicious cycle. Under optimal, non-stressed arousal, your brain is sitting pretty in that delicious cycle. The PFC provides top-down control. It keeps you thoughtful, focused, flexible. But during acute, uncontrollable stress, the amygdala totally takes over. It kicks off a bottom-up, vicious cycle, flooding the brain with chemicals that actually shut down the PFC's advanced operations, switching you over to primitive, reflexive, panic button actions. Now that's great if you need to dodge a falling rock, but it is terrible if you need to remember emergency flight protocols.
Which brings us to section 3, testing spatial working memory, the experimental evidence.
We actually have a fascinating experimental design to quantify this specific loss. It's called the oculomotor delayed response task. This was detailed in the 1989 study by Funahashi S., Bruce C.J., and Goldman-Rakich P.S., titled Mnemonic Coding of Visual Space in the Monkey's Dorsolateral Prefrontal Cortex, published in the Journal of Neurophysiology. In the control condition, a monkey looks at a central fixation point. Then, a brief visual cue flashes on the periphery. Following that is a crucial 2.5-second delay period where the screen goes entirely blank. Finally, the monkey must move its eyes, a saccade, to exactly where that cue was to get a reward. They literally have to use their working memory to hold on to that spatial location during the blank delay.
Now look at the single unit recording data measured here. During that blank delay period, specific neurons in the PFC maintain a persistent firing rate, and this is key, only if the cue was in their preferred direction, say 90 degrees. If the experimental condition placed the cue at 180 degrees, this specific neuron stays completely quiet, while a different one fires. We call this spatial tuning. It's a highly significant effect, showing a strong statistical correlation where firing rates for the preferred direction are maintained well above baseline, which directly drives successful memory retention. You are looking at the literal biological manifestation of a thought being held in the mind.
All right, section 4, cellular chaos in the brain, the Goldilocks principle.
This brilliantly illustrates the inverted U effect, which is so incredibly important to understand. Both noradrenaline and dopamine act on a Goldilocks principle here. Right in the middle of the curve, which is optimal alert waking, they engage high-affinity receptors that amplify the correct signals and reduce background noise. Your mental sketchpad is sharp. But look over at the right side of the curve. Under stress, a massive flood of these catecholamines just bombards the brain. The effect size here isn't just some minor dip. It is a profound, statistically significant functional collapse, where persistent neuronal firing drops all the way down to near baseline levels. The working memory network is completely suppressed.
Let's break down how this builds into total cellular chaos. When there is way too much noradrenaline, it overflows and starts binding to low-affinity alpha-1 and beta-1 receptors. Meanwhile, massive amounts of dopamine overstimulate the D1 receptors. The result? The neuron entirely loses its spatial tuning. It just stops firing correctly. The memory of where that visual cue was, or, back to our macro real-world example, the memory of how to fly the plane is instantly and thoroughly wiped from the working memory network.
And that takes us into Section 5, Inside Neurons Under Stress, the micro-level disconnect.
Let's zoom way in and look at the intricate intracellular signaling pathways. We see how those alpha-1 receptors activate protein kinase C, or PKC. At the exact same time, the overstimulated D1 receptors trigger a massive production of a molecule called CAMP. As the paper specifically notes, this extreme level of CAMP opens hyperpolarization-activated cyclic nucleotide-gated channels, we just call them HCN channels for short, right there on the dendritic spines of the neuron.
I really want you to remember this specific structural mechanism. When those microscopic HCN channels pop open due to that whole stress cascade, they act exactly like a massive leak in a garden hose. The electrical inputs coming from the brain's network are physically shunted. They leak out. The connection literally drops. That is the exact physical, biological moment you lose your train of thought during a stressful public speaking event or an emergency. The connections holding your thought together are structurally disconnecting.
Finally, Section 6, Mental Illness in Society. Zooming back out.
So what happens when this isn't just a temporary freakout? When stress is chronic, the changes stop being temporary. Chronic stress causes literal structural, architectural damage. It rapidly erases the dendritic spines right off the PFC, shrinking its capacity while simultaneously causing the dendrites in the fear-driven amygdala to grow and expand. This vicious cycle gets even worse for individuals with specific genetic mutations. The paper highlights genes like DISC1 and RGS4, which normally act as molecular brakes on that CAMP and PKC signaling. When mutations cause a loss of those brakes, the stress pathways just run completely unchecked, and this is heavily linked to severe mental illnesses like schizophrenia and bipolar disorder.
But it's not just internal stress or genetics. We absolutely have to consider environmental insults. Lead poisoning is a massive one. Lead is a divalent cation that perfectly mimics calcium in the human brain. Because of this, it potently activates those exact same PKC stress pathways we just talked about, effectively putting the PFC in a state of continuous, non-stop biochemical stress. The symptoms of this? ADHD-like attentional deficits, extreme loss of impulse control, and heavily documented statistical correlations with violent crime rates and antisocial behavior.
We can actually see the ultimate macro-level societal consequence of this biological mechanism by looking back at history. We turn to the 1984 study by Woolley D.E. titled A Perspective of Lead Poisoning in Antiquity and the Present, published in the journal Neurotoxicology. This study outlines how the wealthy ruling class of the Roman Empire regularly consumed foods preserved in lead syrup and drank from lead-lined vessels. This massive lead exposure would have triggered these very PKC stress pathways we've been looking at, constantly short-circuiting their prefrontal cortices. The resulting poor decision-making and highly impulsive behaviors at the absolute highest levels of leadership may have quite literally doomed one of the greatest empires in human history.
Which leaves us with a pretty provocative thought to end on today. If our prefrontal cortex evolved to give us thoughtful, civilized regulation, but is inherently biologically fragile to both the neurochemicals of stress and modern environmental toxins, well, is our chronically stressful, hyperstimulating modern world doing to our collective brains exactly what lead-laced wine did to the Romans? Are we structurally disconnecting our capacity for complex thought on a societal scale? Thank you so much for joining me for this explainer, and I hope this leaves you with a lot to think about, while your working memory is still intact, of course.